Hi, my name's Dan, and this video is part of quite a long series in which I'm using a digital electronic simulator called Digital Works to go from the from the principles of simple logic gates all the way through to a 4-bit CPU. And down in the description below, there's a roadmap of where we're going with that. There's also a link to the software that I'm using, which is called Digital Works. We won't show that in this particular video because in this video, we're thinking specifically about a thing called the ALU. So we've got to a point in this series of videos where up until now, pretty much everything has been quite generic and would be applicable across lots of different situations in many different CPUs. But there comes a point where the design of our particular CPU has to start coming into uh, to bring its influence in. And this is that point. So this video and the next few videos are, as I say, about the design of the ALU. And this video in particular is going to discuss how we decide what's going into the ALU and what we're actually going to do in that. So it sets up the next few videos in terms of the practical application of this. So here we go. I guess the fundamental question is, what is an ALU? It stands for Arithmetic Logic Unit, and it's part of a CPU. Uh, I don't actually know if every single CPU has an ALU, but I'd be very surprised if there wasn't one in most, if not all, CPUs. And so those are words that have been strung together. What does it actually mean? Well, it's the maths circuit thing. So arithmetic obviously means maths. Logic is this means it's made up of the logic gates. So therefore it's a digital circuit, and unit just means thing, obviously. So it's the part of the CPU that can actually do calculations. And as we'll see with our design, actually, we're not going to ask it to do many different kinds of calculations, but the way that we set it up means that it's quite versatile. Okay, it works on binary numbers. We need to remember that. That's fairly obvious. Typically, they have two inputs and one output. There's I'll put a mental asterisk against that one output because there's actually some other output stuff as well. Let's have a look at a typical diagram for an ALU. ALUs are often shown as being this kind of fat V shape. And this is a picture that I've taken off the internet. In the credits, it'll tell you where I got it from. And just to explain the things that are going on here. So there are a couple of inputs here, which are the left-hand side and the right-hand side. They've called them integer operands. That's just a fancy word for input. It's basically we're taking two numbers, doing some maths on it, and producing an integer result, which is, I'm going to call the output. Okay, so that's the three basic things that we're going to explain what the other stuff is as well. So on the left-hand side here, there's status can be all sorts of other information. In fact, in the one that we designed, we're not actually going to use this. But we do need to know which operation we want the ALU to do. So an ALU typically can do more than one thing. I guess the most basic ALU is one that all it can do is add two numbers together. But it'd be useful to be able to do more than that. And so you need to be able to tell it what you want it to do to the numbers to A and B. And this takes the form of the opcode, which is a code which tells it what operation to have. And because we're designing a 4-bit CPU in total, then our opcode can be a maximum of 4 bits. So we need to bear that in mind as we're designing this. And then finally, on the other side, I kind of implied that there might be more output as well as the actual mathematical output. There's a thing called flags usually to indicate something about the status of the operation that's been carried out. So this can have information about overflow, and if you know about adders, and I've done a short series of videos on adders, so if you want to watch those and haven't done so, you can do so. there's a carry out in a ripple adder. And so this can become part of the status. There's also, it's quite common to have flags if the output is 0, which is potentially interesting because you could obviously look at the result and see if it's 0, but we are actually going to do that in our ALU. We're going to get the ALU to say whether it's 0 or not as well. Other flags could include whether the output's negative or not, or various other flags there. So let's move on. Yes, I need to say there's a simplification going on here, which is that modern ALUs can be very complex. There's all sorts of things that they can do, and as the hardware has got cheaper and faster, more and more different calculations are being done natively by the ALUs rather than by a combination of programming it using the operations that are available. And also they can become quite specialized. So for example, GPUs, graphics cards, have very specialized ALUs in them, which can natively do pretty much, in one clock cycle, the sort of maths that's involved in graphics, which is to do with matrices and vectors. And we don't need to talk about that right now. So let's think about some simple operations that can be done and that we could kind of see how you would do them using the digital circuitry. So addition, we've gone through that if you've watched the previous videos, and that's a relatively straightforward thing to do. Subtraction actually is an extension of addition. Again, if you don't understand why, then go look at some other videos on that. I will kind of gloss over, but tell you what it is that you need to do. Bitwise AND, which is to take your two inputs and take each bit in turn and do an AND for the output. You can do a bitwise OR. You can also do an inversion, so it's a bitwise NOT, which basically takes all the ones in your binary number and turns them into zeros, and vice versa. You can compare. So if you XOR the two numbers in a bitwise way, if the two numbers are the same, then your output will be 0, 0, 0, 0. And this is particularly useful. Increments, so add 1 to a number, a decrement, take away 1 from a number. Bit shifting, so if you don't know what bit shifting is, it's moving the bits in a binary number so they either become move into one column higher or one column lower. Whichever way you go, you lose some information off one end. But if you take the binary number 101, which is 5, and then shift the bits to the left, and then add a 0 on the end, you get 1010, and this neatly multiplies the number by 2. Similarly, you can do the reverse. So if you bit shift to the right, you divide by 2, but you might lose some precision there because it's an integer division. Similarly, if you bit shift and you had a 1 in the 8s column there, you would lose that. But that's bit shifting can be used as part of various mathematical, more long-winded mathematical operations. Okay, so our ALU, this is not being picked at random. This is after quite a bit of consideration of how to make the hardware fairly simple, but the most versatile that I can think of. We're going to do these particular things. We're going to do addition, subtraction, inversion, comparison, increment, and decrement. So we're not going to do bitwise AND or bitwise or the bit shifting. We'll get rid of the ones we're not doing, and we'll quickly look at how to do each of these in turn. And again, you could kind of work this out backwards. I came across this list by thinking about, well, what could the hardware do? How to make the hardware pretty simple, but versatile. So addition is obviously A plus B, and you need specific hardware to do that. Subtraction, I said I'd kind of gloss over it. I'm not going to go over the theory and the binary as to why this is the case, but if you add A, and then you invert B, so that where there were ones, you got zeros and vice versa, and then add 1 as well. And our adding the hardware can do that adding 1 because it has a carry in. Then this subtracts B from A. Okay. Inversion, inversion hardware is really easy because you just put a NOT gate on each of your things. But actually, we're going to do it in a slightly strange way in that we're going to XOR A with the number 1111. And this brings in the idea that I'm actually going to hardwire a couple of numbers into the ALU to be able to use. So again, I'm not going to go on do in detail why inversion works if you XOR A with 1111. You can either trust me or you can work it out for yourself or be clever enough to actually know that already. You can compare. So this is why I'm using XOR for inversion, is because I want the XOR in there anyway. And I want XOR A and B. So that gives you the comparison. So you can check whether A is the same as B. And if they are the same, then we're going to flag up the 0 flag and the flag outputs. And the reason why this is particularly useful is because a comparison can be used as a condition. And when you're doing programming, there are 3 basic elements that you need to make programs work. The first is sequence, so that you get one thing happening after another. The second is selection, which is where you actually get the flow of the program to change depending on the condition of something that's there. And this is how we're going to, well, it's one of the 2 ways that we're going to do this. We're going to use jumping that is conditional on whether you have a 0 output. And so this is kind of in higher level programming is equivalent to saying if A is the same as B or if A equals B, then do something. And you might want more comparisons than that, but it's tough because we've got very limited hardware and very limited space for operation for opcodes. So if you want more complex things, you're going to have to program them in. Where were we? Right, increments. Well, obviously A plus 1 is the thing, but actually it's going to be slightly strange because I'm going to do A plus 0, 0, 0, 0 plus 1. And the reason for that is because in order to make the add work, I've got 2 inputs and then the carry in. And it's actually, in terms of hardware, simpler for me to just use the same addition hardware, but feed it in zeros instead of where B would be, and then use the carry in. And then that'll give us an increment. And then decrements, what we're going to do is we're actually going to make it deliberately overflow. So we're going to do A add 1, 1, 1, 1, and actually the result for that will give you a carry out because it's overflowed, but the actual number that you get as a result will be 1 less than the A that you put in. So a couple of those are a bit kind of cockeyed in the sense that they're coming at the problem not in the most straightforward manner. But there are reasons for this, and the reasons come down to, as I keep saying, simplicity for the hardware, really. So when we look at these 6 things, we've actually only got 2 operations that we need to have to do, which are addition and XOR. And then we've got, for the second parameter, we've got 4 things that we might want that to be. So we've got the B as it's been passed in. We might want to inverse the B, which we use for the subtraction. And then there's these 2 hardwired values, 0, 0, 0, 0, and 1, 1, 1, 1. It may seem a bit odd and wasteful to have them in, but actually, in terms of hardware, that's really, really cheap, hardwiring those numbers in. And then finally, we also need the carry-in, which gives us the plus 1, which we're going to use both for subtraction and for the increments in here. Okay, so let's have a look at these 3 things then. This is kind of boiling down what we want our ALU to be able to do. So we've got these 2 operations, add and XOR. We know how to do hardware for add. XOR is really easy. Of course, we just use XOR gates. And we want to be able to tell the ALU which of these to use. So the information for that, we've got 2 options, so we only need 1 bit of information. to tell it which one it's going to do. We've got a second parameter, and we've got 4 choices there, so we're going to need to give 2 bits of information to be able to choose that. From our boundary theory, we know that we can express 4 different choices using 2 bits. And then finally, we've got our carry in, which is another 1 bit of information. And altogether, that gives our opcode as 4 bits, which is brilliant because this is exactly what we're looking for. Now, if we had an opcode of 4 bits, there's actually 16 different numbers that you could have there. So I guess there might be a question, why are we not having 16 different operations? And there are 2 reasons for it. One is that um, we could do 16 different things and our ALU would get considerably more complex. We would be able to just use these 4 bits to say add or XOR, and then 2 bits for the 4 different inputs, and then the carry in for 1 bit. And that actually gives us 16 different configurations. Some of those are repeats of the same output, and some of those are less useful. So actually what we're going to do is we're going to cherry pick the 6 that do the things that we actually are looking for, and save the other 10 opcodes to do other things, because we only still have 4 bits, and although we want our ALU to be as versatile as possible, we've also got to be able to give instructions to the CPU to do things like move memory around and do jumps to get our conditional things going on. And very importantly, we're going to need an opcode to say stop running. So a halt opcode. So actually, we're only going to use 6 out of our potential 16 opcodes which the CPU will understand. Uh, Only 6 of them will be things where the ALU actually does anything for us. So let's have a look at what hardware we're going to need in the ALU in order to achieve these things. So fairly obviously, we're going to need an adder. We're going to need a bitwise XOR. That's just going to be 4 gates. That's going to be pretty straightforward. And we need a way of choosing which one of these we're going to use. And one way of choosing, which is quite cheap in terms of hardware, is not necessarily the cheapest in terms of power, but it's a legitimate choice for us in the size that we're working, which is to actually do both and then choose which output we're going to use. So we're going to use a 1-bit multiplexer to choose the output. We're going to feed our inputs into both the adder and the bitwise XOR and then choose which output we're going to use. We're also going to want to do things for this in terms of making the choices for the second parameter to choose which one of those we're using. So obviously, if we're using B, then it's fine; it can just go straight through. If we're doing subtraction, we need to invert B, so we need an inverter. Again, that's really simple hardware because it's just not gates. We're also going to want a hardwired 0, 0, 0, 0, very, very easy. A hardwired 1, 1, 1, 1. And then we want to choose one of those 4. And again, the simplest way of doing this is to actually provide all 4 of these things and then use a multiplexer on the outputs with a 2-bit multiplexer to choose which parameter then is actually fed into our adding and XORing hardware above. So if you've been watching these videos in sequence, then a few videos ago I was talking about some general design principles for CPUs, and I decided that for this design process that we're going through, that when an element has an output, I'm going to make if that's appropriate, I'm going to make the register for that internal to the hardware. Where I have inputs, I'm not going to. And this has worked for me as a general principle, so I'm going to stick with it with the ALU. Basically, you don't want to do both just in case one's feeding directly into another and you end up duplicating too many registers. But also, if you actually internalize the registers into the pieces of hardware, it makes more and more of your elements look like bus-ready pieces of hardware, so you can just connect them directly to the bus. So in terms of our outputs, we've got a couple of things to think about there. We've obviously got the actual output from the from the calculation. So we're going to have a register to hold the results for that. And we've got these flags that we keep talking about. So we're going to have a separate register to hold the flags, which we'll then be able to read from other places. Okay. So that's a bit of a rundown. If you're still confused as to what's going on, don't worry too much. Over the next few videos, we're going to start and take these ideas and turn them into the actual, actual hardware, the simulated hardware using digital works that will be the ALU for our 4-bit CPU. But that's it from me for now.